So this is about a work of Bowditch. So his original paper contains so many ideas, and from one part of the paper there has been a lot of progress on the study of the mapping class group acting on the space of representation and trying to describe a subset where the action is nice. Okay, and so what I'll try to do in this talk is explaining a little bit the motivation around the question that we will look, and then explaining some of the ideas that come and some big ideas of the group. And then tomorrow we will see what we have to do when we try to generalize verbs. So, okay, so for the talk today, we will have a group. You can think of a surface group, free group, three-manifold group. Mostly we will, for the talk today, we will stay in these two sets. In fact, mostly here. And you can think of, and you need to have a D group G, the target group, that for the talk today will be mostly ESL2C or SL2C, but you can also think of compact group, SE2. And so the character variety, like for us today, you just should think of the conjugation classes of representation. Homomorphism from gamma to G up to conjugation. Okay, I already I call it a variety. This is not a variety in general, like the way I define it. Might not be Ausdorff, but for the question that we will discuss, the dynamical question, the difference between this space and what it's usually called the character variety is it doesn't matter. Zero, so and please stop me if you have any question. Sorry? No, I think like today, yes, maybe we do SL2, but tomorrow we will discuss well SL1 that is again rank 1, but there will be an SLD that I will mention, but yes, so for today mostly yes, but you can. And which is the group that is the outer automorphism. So automorphism up to inner. Again, this is the group that is good to consider when you act on these conjugation classes. And so this will be the question, the object that we will look today, and basically we will try to answer what can we say about this action. Okay, so like the first thing that I will mention is that if you take a orientable surface, you can see that there is a dichotomy of behavior, like if the target group is compact or if the target group is not. So if the target group is compact, then it is a result of for a surface, an orientable surface group, and here, like I should say that here the action, if you think about the surface with puncture, you think about the mapping class group that I will introduce. Second, I think this is the notation I use later. And for the free group, you think about the action of the outer automorphism, and this action is ergodic, and like we have seen this work coming up in diagram talk. So the only invariant measurable, the only measurable set that are invariant are the empty set of the space. Yes.
This is strange. sphere and first for groups and the acting sort, but
Yeah, so we will see for the discussion that we will have today, where we will focus on the torus with one puncture, then the mapping class group and the out F2. In that case, I want the fundamental group. They will not be much different. One is a finite indexing to the other, and so considering one action or the other for the person doesn't matter. But when you just go, that is just a very ad hoc case. In all other cases, those groups are much smaller and they behave in very different ways. So, the idea that you will see in the non case is to try to build domain of discontinuity, but for different groups. They are all subgroups of the same interval, but they will be different. So again, this will be not the direction of the talk today. I just want to mention that, even so, Goldman discussed the case of SU2, Pickrell and Xia generalized general group, and even if you try to generalize to non-orientable surfaces, this is mostly unknown. And in fact, like for the orientable case, like I didn't discuss, but I didn't went into the details of what is the measure that we have the variety. But Goldman defines a symplectic structure on the variety, so the method is associated to that. But when the surface is non-orientable, you don't have a symplectic structure. So even the definition of the mesh is but when the group is not compact, that will be what we will focus on today. There are domains. There are open sets where the group acts properly discontinuous. And so, like these are the tail action. And this will be the aim of today.
Is that a stratified set? You go set.
So, I don't, so I don't think in these cases much is known like about the simplification of the boundary. I think a lot of the questions are still open. Like I will mention, for example, for a closed surface and PSL2C, like conjecturally, the domain of discontinuity, the maximum domain of discontinuity is just quantity spaces, just compact, and the boundary of this set is known not to be contained in any domain of discontinuity, but is still open if maybe the set is not contained. But I think very soon we arrive. So so for today, the group today will be SL2C. And for if we consider a closed surface, then like a theorem tells us that we consider in that case the mapping. But the mapping class group is finite index in the outer automatic. And so Friedman show that maybe you are familiar with the fact that the mapping class group acts properly discontinuously on techniques. And so his proof of this fact actually proves much more. It proves that in general, like the mapping class group acts properly discontinuously on convex to compact representation. So what are convex and compact representations? They are representations such that I call it a d-orbit map or any orbit map. It's the map that maps the group into the image. So you pick a point in H3 in this case, and you map gamma into the image of P under rho of gamma. And so this will give a map from the group into H3. And so if this map is a quasi-isometric embedding, this is compact representation. And if you come more from geometry, this also correspond to quasi-Fuchsian representation, like the formation of discrete faithful representation in PSL. See, and the +2 formal automorphism. And another way to say is also the interior of the set of discrete faithful representation. So, and this story will be true like if you 3 minus 2. This theorem of Fricke always tell you that this action is nice, is tame on convex compact representation. And in fact, in this setting, a conjecture of Goldman is that the complement of quasi-Fuchsian space, the action on the complement is actually a and this is still open. What is known is that no point in the boundary of convex compact representation is included in any domain of discontinuity, but is still unknown if the domain of discontinuity can be disconnected. And that in general is the question when people try to understand the maximal domain of discontinuity, I think that is not known. There has been maybe paper published with some wrong results, but then they realized. Any question? On the other hand, when the group is the free group, the story becomes maybe even more interesting. So we still have, as I was saying, the theorem of Fricke that autofan acts on convex compact representation. So again, if you are more of a geometer, in this case, convex compact representation corresponds to Schottky representation. So hyperbolic structure on the head, or the interior of the discrete field. On the other hand, Yarminsky, now probably 15 years ago, he showed that there exists a domain of discontinuity for this action that strictly contain convex compact representation. And this is a set of primitive stable representation. I will define, actually I can define it now. And so his idea was to consider this definition of the set of convex compact representation, and instead of asking the whole orbit map to be a QI embedded, he decided to focus on axes corresponding to primitive elements. Okay, so in Fn, a primitive element is an element that can complete two bases. So for example, the free group in free generators, A, B, and C. Like AB is a primitive element, but the commutator of A and B is okay. So you look at the Cayley graph, you look at all the axes of corresponding to primitive element, and you want your orbit map to map all these axes to uniform position. And in his work to show that this set is open and the action of outer fan is properly discontinuously is not so hard, but what is really much harder is to show that this set strictly contains convex compact. So he had to use the theory of what was known about points in the limit of Schottky representation and show construct an example that is. Okay. So this is a little bit of the motivation to just say why should we care, why these things are interesting, and so for today we will focus on one particular case, but before, maybe I just want to say the general refrain that I hope can stay in your head is where are these domain of discontinuity coming from? This domain of discontinuity in the non-compact case comes from geometric structure. And so like in the case of PSL2R, it comes from hyperbolic structure on the surface. PSL2C, it comes from the deformation in PSL2C, so quasi-functional space. And so this is the higher rank that, so this PSLDC, PSLDC or PSLDR in this case, each represent. And yeah, for PSLDC, like the space of. Okay, but today we'll focus, at least the talk today will focus on one surface, the one punctual torus, and the one group, SL2C. Okay, so we'll be very concrete and we will try to build the theory and then see how to generalize it. So, okay, so the one on torus, I will sometimes pass between thinking of S11 as a one-word torus or as a one punctual torus. So hopefully it will be clear if you if it's not clear just that. But just since we were mentioning like A alpha and beta, I call two generators, and in that case the commutator is the peripheral. And one fact that will come up is that in this case, actually, all simple closed curve correspond to primitive variable. Okay, this is one of the few cases where primitive variable. Okay, so I keep talking about the mapping class group, but I will always consider when we have surfaces with boundary the pure mapping class groups. We will always consider homeomorphism of the surface that fix the boundary. And so in this case, the mapping class group is generated by the two-dent twist around the two curves, alpha and beta. And the character variety that we will focus on today is representation from F2 into SL2C. So again, one fact from Vicky is that this character variety can actually be parameterized by three complex. You will see that a lot, so all these varieties are characterized by traces. And so in this case, you can send a representation in the triple that correspond to look at the trace of row of alpha, trace of row of beta, the two generate, and trace of row of alpha beta, the product. And yeah, the mapping class group action, again, we have the group. Like I forgot to say before, like these, it acts with the inverse adjustment. And so, because we will always consider the pure mapping group, it preserves what is called the relative character variety. So, representation where the trace of the boundary is fixed. Tau any complex number, and so like when you act by the pure mapping group, this trace doesn't change. And so here, like we will look at the set of triples in C3, where this equation will be satisfied. And so the Bowditch set, like I define it in the way that Bowditch originally defined, and we will see how to use this definition and how this definition can be then translated in many equivalent. So yeah, the way that we originally defined it is that what do we ask? So first we ask that if you take any simple curve, the trace of row of that simple cluster is not parabolic or linear. Okay. And the second question, the second condition that is maybe more mysterious is the fact that if you look at simple cluster with the trace bounded in norm by, then you only want a finite number. So yeah, this second condition is more mysterious, but we will see how this condition comes up. And some of the other way to characterize this set are maybe more intuitive to understand, but they are harder to work with. And so this, with this notion, it's easier to show that this set will be open and the action is properly. So yeah.
So first thing is saying the traces are outside of the simple, but then doesn't that imply there's a second step? Oh, okay.
That's it.
Oh, it makes sense.
Yeah, these are complex numbers. We are removing just the real interval, but we also want the radius around the radius 2. And in fact, we will see that in other cases, this 2 is special to this case. In other cases, it may be. Yeah.
That's the determinant. Force.
No, so these are all, we are all in SL2C. Yeah, we are in SL2C, and here we are asking with this first hypothesis, we don't want any parabolic or any element. And with the second condition, yeah, it's more mysterious to motivate why, and hopefully we will see in the talk why that comes. But we just don't want too many elements with bold place. Other question. Thank you. And so, yeah, what I will focus on today is the original paper of Bowditch, Markoff paper in the quantification groups. And he studied the case of the one functional torus. So for him, tau was equal minus. These are type preserving representation. And then Tan-Wong-Zhang generalized this work in generalized Markov map and vector. Yeah, we will see the word Markov map come up, but with collaborators, we stopped putting that word in our abstract because actually people were coming thinking about it. We get it very different than this. Yes, will not be. You're thinking about the Markov map that you know probably this will. Okay, and so what they do, one of the things that they do is that this Bowditch set is a domain of discontinuity for the action of the mapping class group on the character variety. And if I stop here, you should complain because if I stop here, you're saying, well, okay, we already know that convection compact representation is a domain. So what they really prove is that actually that strictly contains the set of convection compact. So one part is that I say it strictly contains the set of convection compact representation, and that is true if you consider a general. So here I just wrote the general character variety. But if you fix a single boundary value, so if you consider like the trace fix and you look at the Bowditch set in that slice, it is not actually known in general if for root value if that set is strictly big. And in particular for the case -2, it is conjectured not to be true. So for the case x tau -2, it is conjectured that the Bowditch set is equal to the quasi. trace, and that is why this is PQ is for Bowditch, the Q set. I think if you read Bowditch paper, we call it the Q set, because yeah, so for the whole character variety, that's not nice. Yeah.
But for somebody's a tie, we know.
Because we will see that in fact, contain a primitive stable representation, so that's maybe a way to see. And in general, just a clean change, like okay, in this case it doesn't work, but in F3 and so on, just looking at hyperbolic structure with action in the boundary, those are element examples. Okay, so going back to the relation with the primitive stable representation. So a primitive stable representation, as we said, is a representation is primitive stable if, when you look at the orbit map, the axes of primitive elements are standard with quasi-geodesic, and XPF is exactly the set of representation. And so it's not too hard to show that primitive stable set is contained in Bowditch set representation. I think Greek has a nice way it's using the stable translation. But actually in this case, so it was a question for a long time, like the is one bigger than the other. And so it was a recent result. So that actually for us, primitive tables are exactly the set of Bowditch representation. And so this was proven by Caroline Davis and me and Williams at the same time using different methods. And then Van Fleet, that is now a postdoc in Grenoble, he generalized, she gave an alternative proof of the result, and she generalized this proof, defining these two sets for representation where G is the isometry group of the delta eigenvalues. And in fact, I will mention tomorrow something else. Yeah. Okay. So, okay, so we have this parameterization of the variety and three complex number, and using the trace equation in SL2, we can write it down explicitly what is the trace of the commutator. Again, if you get bored, you can try to find this equation. But okay, so the trace of the commutator is written in terms of the coordinate is this quadratic. So x squared plus y squared plus z squared minus x t minus. And so this is the equation that we will fix equal tau. In fact, we will just usually write it like that, or like equal to plus tau. And so when we restrict to the relative character variety, so the variety where the boundary trace is fixed, it's triples where this equation is. So I just go on one last tangent before going back to the topic of today, is that I wanted to show this very nice picture in a paper of Bowditch, where it was exactly looking at this equation for various value of k, but it was looking at the real point for this equation. And you can see that the topology of this variety varies a lot. And in fact, he even described precisely the dynamics on the various classes, depending on the value. Okay, so again, this will not be the topic of today, but I just want to mention very beautiful paper. Times are interested that. Okay, and in fact, yeah, so when you have these compact pieces, the action will be ergodic, but then you have these non-compact pieces where the action is. Okay, so come back. So today, one of torus, it will be important for us to work to the condition from the Bowditch set is using simple curve. And so, like, and we define the curve complex, and then we will look at the dual. So, what is the curve complex? So, is the which is a flat complex. So, once you understand the edges, then fill in the pieces. And so the vertices pre-homotopy class of non-peripheral, non-trivial things. And you put an edge between two curves if they intersect minimally. So the torus if they intersect once. And you put faces if you have triples that pairwise intersect. And so what the picture, well, the picture will look a lot like that, but so I will mention that the next slide, but this is a slide, is a complex defined differently. Like here you put the vertices as rational number, union infinity, and you put an edge between two rational numbers. If when you look at the determinant between the two fractions, this is plus or minus. So these are two different pictures, but like it's always you always think of it inside the hyperbolizes. Okay, and so yes, I mentioned the graph because actually this is the third complex group, the one on top. And the identification between the third complex and the paragraph depends on a choice of generators for like when you choose a pair of generators, you can choose one to be infinity, one to be one, and then you create everything. In fact, like in this case, you really can write all the words really by doing product. So here you have alpha, here you have beta, here you get alpha, beta, and so on. So alpha, alpha, beta, here you have alpha square beta. And yeah, so here I wrote in terms of the Fourier addition. Okay, so, but today we will care about the dual graph of the Fourier graph. So it's a graph that has vertices, one vertex for each face, and then you put an edge between two faces if they are adjacent. So the edges will correspond to the edges. Perfect. And then you have these faces that have infinitely many edges on the side, and those each region. So if you think of H2 minus your dual graph, you have this region, this infinite-sided polygon that correspond to a single sequence. And so we will see that actually this dual complex has a geometrical meaning in terms of ideal triangulation. And to see that, we need to see that in this case, for every simple closed curve, there exists exactly one ideal arc that is this geometry. Okay, and so when you have a vertex of this dual graph, this vertex correspond to three simple closed curve intersecting once, and so for every simple closed curve you get an arc, and so three of these curves or three of these arcs, they give you this ideal triangulation, and so it's probably easier to see here. And I don't think that this point of view will be important today, but I think it's I think it's nice. And unfortunately, this is not something that easily generalize to also This is a very low dimension. Yes. Yeah, so so every time you have a simple cluster, you have an associated ideal arc that does not intersect that simple cluster. And so let's say if I have this, we have this. If I have blue, then I have this curve here. And so what in the picture before we were doing is that when you have three simple closed curves that pairwise intersect once, these correspond to an ideal triangulation of your torus. So if I draw the torus like that, so I'm going to draw. So this is a one functional torus. So I'm identifying opposite side. And so if I have a simple closed curve like this, then my ideal arc, well, here it looks like 2, but is identified. If I have a simple closed curve like this, again, it's 2 curves identified. And if I have this is yeah, I think yeah. Maybe I wanted, and oops, no, I wrote it in the wrong picture. And again here, and we are. Yes. And what the picture below was saying is that an edge corresponds to flipping, because an edge corresponds to change one of the 3 curves, and so what corresponds to flipping one of the edges. So like in this particular example, you are flipping this ideal arc with this ideal arc. Other question? Okay, so one of these nice idea of Bowditch is that okay, so we have seen that we can identify this relative character variety with the triple satisfying this equation, and so he wanted to identify with the whoops. That's not what what he wanted to identify with the Markoff maps. So the maps from a simple cluster into complex into three that satisfies certain equation. So what do you want? You want that. So here you should think of the map here. You are putting a complex number for every region that you get. Okay, and what do we want? We want for every vertex the complex number. So I'm using the convention that curves are capital letter and the smaller letter are their value, the image. And so the little x, little y, and little c need to satisfy the equation, this equation here. And then for every edge, so the equation that the edge satisfied is given again by this equation, because if you look at this equation and you fix y and z, this is a quadratic equation in x. And the sum of the two solutions is exactly right. The sum of the two solutions is exactly given by this term, by the 1 degree term, and it's y times. And so, like this was a nice idea that with understanding the domain of discontinuity. So this is just one example, and maybe because we are doing a lot of identification. So what is the map? If you start the representation, is the trace. Okay, so one thing to notice is that every time, so now I'm talking in terms of Markov map, but you should think that the data of the Markov map is the same as the data of a representation. Every time you gave me a Markov map, this defines an orientation on the edges of my graph sigma, because you go towards the complex number with smaller ones. And again, the action, so yeah, we care about the action of the mapping, but the action that we really consider is the action by these three involution, theta x, theta y, and theta z, that are the involution generated by sending one solution of the equation when you fix y and z to the other solution. And so the mapping class group is a finite index in this. In fact, the product of two of these two distinct involutions generate the three dentries around the three curves. And okay, this is I'm restating the Bowditch set. Okay, so I now want to try to give you a sense of the, and so the idea of the, so we are trying to prove that the Bowditch set is a domain of discontinuity. So we want to prove that the set is open and that the action is a problem. And in fact, really the crucial point of the talk will be really to prove that representation in the set have the property that so a representation defines an orientation, and so it has the property that you can always find in attracting tree. So it's a subtree that such that all the edges point towards it, but this attracting tree in this case it's fine. Okay, so for every representation you can find an attracting tree, but only for the Bowditch one it is fine. Yes. Yeah, sorry. It's like you put an edge.
It's bigger.
Yeah, when it's yeah, you go towards this. Yeah, smaller. Like, again, they are complex numbers, so we compare them. Yes. Yeah. So x, y. So the map that we have gives associated to a region a complex number, p of x and p of y. P of y is little y, and so you go towards the smaller. So y is smaller than x. And so I put here strictly smaller, so these are complex numbers, so these are just. And so when the norm is equal, you choose the orientation that you want, but that won't have. Other question?
So orientation is guaranteed by the equation that you had before about the relationship to the numbers.
Yeah, so exactly. So if you have a representation, like you map every simple curve to their traces, and then you compare the norm. So if you go towards the smaller, if they are equal, choose as you wish. Like we care about the asymptotic behavior. So if you maybe we do a different difference, it might vary. But other question. So this will be the big part, because once we have that, the openness and the proper discontinuity will really come easily, because like we will show that it is open by seeing that if you vary the value of the function a little bit, the attracting tree will be finite and hence. And similarly with the properties. And so how do we prove these equivalence? So there are three main steps. One would be a fourth lemma that will give the connectedness of the. So these are the region. So these are the simple closed curve such that the trace P gamma is less. So we want to prove that the region of a simple closed curve with more traces are connected eventually. So given. We need to analyze what happened to the traces or what happened to this function when we look at the traces around the region. So around the region, the traces will be given by the dentist movement. And so we will prove that in many cases, this trace will grow exponentially. And this exponential growth is exactly what will allow us to define the attractive. And finally, we will have to compare the growth of this trace with the word length associated. So this will be step 3 in this Fibonacci. Okay. So, like, hopefully I will tell you some of these steps, and if not, I'll see. So I just wanted to break it down concretely, so I choose a simple result, but because I think it's nice to see the type of it's like, so the first thing that we have to prove is this fourth claim. So we show that if in the orientation of the tree, you have a fork. So a fork is that you need 2 edges that point away from a vertex. Then, either is norm is less or equal to, or is 0. And so, here you really work with the inequality coming from your vertex and your edge equation. And the fact that when you have an orientation, so if you have this orientation, this tells you that y prime is less or equal than y. And so you have this inequality, and here you use the triangle inequality, and here you use your edge equation. And similarly for z, to see that the product of x and z is less or equal than 2y and is less or equal than 2z. And when you plug in, you obtain just this inequality, and you know this is positive. And so really can see that either this is negative or this is. And so once you have that, you really now understand the connectivity of this region. So you, again, we have our region, and what happened is that you might have a blob here and a blob here of region with the Markoff trace small. And so what you do is really you use contradiction, and you say, okay, so if it is disconnected, then there is a path between them. And so, but these are small traces, so these tell us that the edge here need to be going towards, and here need to be going towards, so you need to have a fork. And this is where this fork lemma comes into play, to really see the connectivity of this. Step 2 is what I was saying, is that you need to study how the traces of curves varies around the region. And so here again, you write it down using the edge equation, what the general form of the traces is. And you see that in many cases, so when the value for this function is outside our real interval -2, and these exceptional cases, the plus or minus tau plus 2, then is grows exponentially in both directions. So this is the good cases. And then there are the cases that we will need to be worried about. So when it's in the open interval -2, this sequence is bounded. When the trace is equal to plus or -2, then these grow only linearly. And when one of these values, you have this the fact that it has a. And so again, these will be the cases that we will have to exclude. And the other thing that I have to exclude is escape erase. So we need to try to understand if we have a path of a geodesic where you look at all the pointing arrow, like how these behave. And so in that case, we are able to prove that either it eventually lies in the boundary of the curve, or it meets infinitely many region with the small trace. So I forgot. Either eventually lies in the boundary of the curve with the small trace, or it just is infinitely many, because remember, like you keep pointing towards the small cases. So if you don't lie in one region, then you keep meeting a new region with. So this will be bad. So we won't want. And the last things, and then I stop, is this Fibonacci function that will allow us to predict the growth is the trace function with the word length. And so we define a function that we call the Fibonacci function, where from one edge we define 1 and 1, and then you just do the Fibonacci rules. You define 1 plus 1, 2, 2 plus 1, 3, and so on. And why this is, why should we care? Because if you think about the original word, this Fibonacci function is exactly the word length of the curves associated with this. And basically for every representation, you always have this upper bound of the trace function in terms of the Fibonacci growth, but only for the Bowditch set. You have the and yeah, this is how we are able to show that the tree associated is finite and has. Thank you very much.
Thank you, Sara. Do you have any questions? We have time for a few. There's so many here.
I go. It's like an analogy.
Very fast.
Yeah, an analogy of type your fast, in your space, like. What are like quotients for like these different domains of discontinuity? Like,
I don't know. I actually, yeah, I have no idea. Yeah, I never, yeah, never thought about that. Yeah, I'm not sure how easy it is to understand, because you don't have a good geometrical meaning for this representation. So yeah, I think I don't know is probably the best answer. I think, yeah, it will be nice. Yeah, if one can understand it.
Question?
can you say that word? Three,
Yes.
so
Yeah.
to get some sort of growth, like the. Of these, pieces, you go out these branches.
Yeah, so like what, yes, what you.
Oh,
Yeah, so
yeah.
so the question was that, yeah, can you say a little bit more about this? Yeah, so what, yeah, I think I didn't understand. So what we do is that, so we define this notion of Fibonacci growth for a function, and the function that we consider, so this is our function that you can think as the trace. And so we consider the log plus, so the maximum between zero. The maximum between 0 and log. And what like what you show is that like the upper bound is really like the finite generation of the the upper bound is always true. And so for the lower bound, yeah, so we have to work to show that actually with all the tools that we built before, in that case, we can find the lower bound. Like, so we can prove that when the function has this finiteness of small traces, actually you can use that to have this finite lower bound. And with this behavior, then we are able to show that in this case, the Bowditch representation are exactly the one where the attracting is an outside. And basically, when you show that, and so, yeah, I think some of these arguments are really building up the equation that you have and try to play the equation and find the bound. And in fact, when you try to generalize this method to other cases, yeah, in this case, you have this nice equality ideal triangulation, a simple curve of things works well. This doesn't work so well in general. Yeah, the idea is that okay.
I think we can keep for the time, thanks, Sarah, yeah. Great news, if you love that, there's part 2 tomorrow at the exact same time, 1:30. And also if this made you want to join the reading group based on what Sarah talked about, remember, you can just send us an email, we'll sort people into, I mean, you'll sort of be the last minute group, so we'll put you in a group, we're happy to have you for this semester. What should I be saying? We have a break, I said, Laura. Snack?
Here, we have a welcome meet and greet, so for everyone who's new to UAC, every Friday, we run a welcome. We're running welcome, we put snacks and things, and meet and greet the speaker, we have questions, in this case, Jeff is our first speaker speaking today for the conference and welcome, so you can ask Jeff questions and get to know whether you want to see the pattern, anything you can think of, you can take this opportunity to ask him during the next half an hour. We're going to start at 3 o'clock and then at 3:50. Thanks, Sarah.
Hey, we'll be leaving the meeting, but we'll be back at 3 for colloquium.
Sorry, I should.
Okay. Great,